So this is a plot between the depth and the magnitude of the earthquakes. So when you see this, I had chosen a depth from 0 to 300 and a magnitudes of 1 to 0 to 9. So when you observe this particular graph, there is an earthquakes, almost all the earthquakes happen around 0 to 200 depth in this particular Trinidad and Caribbean region. So when you see the devastating earthquakes are considered from magnitude 6. These happen in a range of 0 to 150, the most of the earthquakes, and there are very less number of earthquakes happen on 6 to 8, 9 scale of a Richter scale of a magnitude. But when you consider there is a maximum earthquakes happen from 3 to 5.5 magnitude. For the selection of features, I had used attributes correlation heat map to find out what are the features are correlated with highly correlated. One means highly correlated, 0 means not correlated at all, and -1 is negative correlation. So by observing this, I had chosen the features according to this. I had used SVM. So SVM stands for Support Vector Mission. In that, this particular SVM model can be classified into two types. One is classification and the one is regression model. So when considered to the earthquakes are not considered falls into a regression model, where to forecast or predict, then we have to go with a regression model. So I had taken a SVM and I had transferred the data from CPUs to GPU, and where the SVM calculation or the regression model happens on the GPU, and once that is done, the GPU transfer back the data to the CPU. To classify the new data points, I had used this particular formula, and to consider the performance evaluation for this criteria for the accuracy, I had used this particular formula. Accuracy is equal to TP plus TN divided by TP plus TN plus PF plus FN. So what are those? Are true positive, true negative, false positive. So I had considered this. So and then I had calculated those values and to find out what is the accuracy of my model. So when you see the results, I had considered the three types of support vector missions from scikit-learn and the other SVM, the other two SVMs which I had developed. The lib-SVM is from the scikit, and GST SVM and H-SVM are two done by me. So I had considered 44 features of each model. So 45 features for the each model. So this 45 is having totally of 690 elements are present in the each model, each feature. So that the time taken by the CPU is 15 seconds for the lib-SVM OMP and 13 seconds for GPU. There is no drastic change when I had taken a scikit-learning model library and I developed. There is only a small difference or the small variation present in this. And when I started going with GSTVM, the first model which I had done, so there is 11 seconds taken by the CPU and 10 seconds taken by the GPU. But when it comes to the hybrid SVM model with a neural network, so I had considered the same 45 features, and the time taken for the CPU to run is 8 seconds, but the GPU took only 2 seconds to train the model. This is an output of my model. So what it's going to ask is, like, it asks for the enter the latitude, longitudinal, the depth, and the day, when and where, at what particular depth, and earthquake happens. So when we enter these values, it generates an output, and this is an forecasted at magnitude of an earthquake happens on that particular day. So, in the previous slide, you had seen the training scores and the cross violation losses. From that, I've just drawn the learning curve, and it's in a learning curve. It'll be on a one on the scale of one. So, how the learning curve improves its accuracy score over a training set period, training size. So you can observe that after a 400 and 500 to 800 training sets, my accuracy has been increased to 95%. So with this, I can conclude that a robust multi-layer prediction model is generated in a combination with the computation of maximum obtainable seismic features, and seismic features are computed. The separate future selection is performed in every region through the maximum relevancy and the minimum redundancy approach. The selected features are employed for the training of the earthquake model prediction. The model prediction model consists of parallel support vector regression model followed by hybrid neural network. The SVR provides an initially estimate for the earthquake prediction, which is passed to HNN, that is nothing but hybrid neural network, in an accelerator predicting in the combination with the futures. These three different neural networks are performed further employed along with EPSO weight optimization. The model is trained and tested successfully. And for the other reasons, to check with the thing, I had checked with the other three reasons as well. So we can check with that. Thank you. These are the references I had used.
All right. So do we have Manoj online to field any questions?
Yes, sir.
Yeah, I'm online. Please go ahead.
Okay.
Good afternoon, everyone.
That's a really good presentation. That's excellent with Manoj.
Thank you, sir. Thank you.
So far, I was off a little bit, right? And I can only see one question right now, and that's from Arshad. Would the machine learning capabilities of the newer NVIDIA GPUs benefit this research?
Definitely, it will definitely benefit a lot, because nowadays the training data is going on gigabytes of data. So to parallelly transfer, to execute it or to find the patterns in the data, the GPU will help a lot. That's for sure.
Okay, and your work is scalable on different architectures, including NVIDIA and others?
Yes, I got your question. Like, only the thing is, like, NVIDIA is not reverse capable. Like, I had developed within a CUDA 9.2 version, so it cannot be scalable on 6 or 7. And when it comes to the across platform, like AMD or any other graphics, it is not a crossover. Like, for that, we have to go with OpenCV or OpenGL libraries. Then this work can be cross-platformed.
Okay, all right, good. In terms of your work on accessing the platforms, you want to describe how you were able to do that? Because I know that in this field it's a little bit challenging to get certain resources.
Can you come again, please? I didn't hear you properly.
How were you able to execute your algorithms in terms of the hardware? The availability of the hardware, or did you have to farm it out to somewhere else outside of the region?
Oh, okay. So right now I had developed this model on GeForce 1050 Ti model, and it can be scalable, and we can send this particular data to any platform which is greater than that. So the CUDA architecture is common.
like it is not varied from one particular architecture. I mean, like one particular, suppose I'm using on 1050 Ti. So if you want to execute this particular program on 1060 or 1070 graphics card, yes, we can do that, and we can just transfer. We can download the data set from the websites and free sources like Kaggle and UG. I mean, American Society for Geographical Center. From that, we can download and we can easily execute this code on anywhere else in the cross regions.
Okay, good. Now, what's the point in using parallel processing for earthquake forecasting?
Okay, so the main problem is like in SVMs and all, any machine learning model takes a little bit of time. Okay, for suppose my model is taking 45 into 6,000, sorry, 45 into 690, that is nothing but 300,000 data. It is transferring it. So if you are using a less computational, I mean, if it is keep on increasing, like going on, I mean, this particular amount, 300,000 data is taking around 11 to 12 MB. But when I was performing this same experiment with the Kaggle, from the Kaggle computation website, I had downloaded a data set which is of 10 GB. It took almost 2 to 3 hours for computing in normal CPU. But when I consider the same data set and executed the same model, it took only the 10 to 15 minutes to complete data set.
Okay, good, excellent. Well, I'm not seeing any other questions, and it's 1:15. Graham, you want to lead into the other presentation?